Hi guys, so today I'm presenting our computer networks project phase 2, and for our group we have Zheng Jialin and Yao Wei, and so let's just go straight to it. Okay, so for the multi-threaded server requirement, we implemented a worker pool with 10 POSIX threads. So at startup, the server creates 10 worker threads, and then each thread runs the worker thread function and waits for a task. And the worker thread function here is basically just each worker locks the queue mutex and then checks if there are tasks, and if the queue is empty, the thread waits on a condition variable, which puts it to sleep. And when a task arrives, one worker wakes up, grabs the client file descriptors, and process it. And so the threads are reused and not created per connection, so it's efficient. And as we can see here, this is the main loop for adding tasks. So the main thread accepts new connections in a loop. When a client connects, we lock the queue, push the connection onto the task queue, signal the condition variable to wake up one worker, then unlock. Okay, so for the encrypted chat message logic, so say Alice wants to send a message to Bob. She would first have to ask the server for Bob's IP and port, and then she would have to send a peer command with Bob's ID, and the server will respond with Bob's connection information. And then after that, Alice would create a socket and connects directly to Bob's listening port using the IP and port that she received. Okay, so for encryption, I use OpenSSL's EVP interface. So each client generates a RSA key pair when they start, and the RSA keys are used for asymmetric encryption, specifically for exchanging session keys. And for the actual message encryption here, we can see that we use AES 256 CBC, so each peer-to-peer connection generates a fresh AES key and initialization factor using OpenSSL's random number generator. So this ensures every session has a unique key. And for the message, each message gets a fresh IP. So before encrypting, I generate a new random IP, use it for encryption, then append it to the ciphertext so that identical message can produce different ciphertexts and prevent pattern analysis. And for the key exchange, when two peers connect for the first time, one generates a fresh AES session key, encrypts it with the other's RSA public key, and sends it. So only the recipient can decrypt it with their RSA private key. Okay, so for the group chat requirement, basically for the creation of the group, the client requested from the server, then the server will generate a fresh AES group key and encrypts it with the creator's RSA public key, and the client decrypts it with their private key and stores it locally, and then this group key is used to encrypt all messages in the group. Okay, so for encrypting group message, when sending a group message, the client encrypts it with the group's AES key. It's important to lock the group mutex lock here because multiple threads might access group keys, and after encryption, the client sends the ciphertext to the server, which relays it. The server never has the group key, so it can decrypt the message, and this provides the end-to-end encryption. Okay, so relating to group chats, we also support commands that let user join or leave a group chat. And the rekeying mechanism is basically when someone joins or leaves a group, the server generates a brand new AES group key and encrypts this key individually for each remaining member using the RSA public keys, and then client receive a group rekey message asynchronously and replace their stored group key. So this ensures that former members can decrypt new messages, and it provides forwarding secrecy. Okay, so for the file transfer requirement, basically we do a safe check first, check if file exists, the file size, yada yada yada. And for the file transfer, basically I split files into 4 kilobyte chunks, and then the sender reads each chunk, encrypts it with the P2P session key that we established, and send it. And after each chunk, the sender waits for an acknowledgement from the receiver to ensure reliability. And this encryption used the existing P2P session key, so we don't need to exchange new key. For the receiver side, basically they open a file then loops until all bytes are received. For each chunk, it decrypts using the shared session keys, write the plain text to disk, and then sends an acknowledgement, and then continues until the complete file is received. Then the file is saved with a received underscore blah 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 prefix. Okay, so for audio streaming, I parse WAV files dynamically. Instead of assuming a fixed structure, the code searches for FMT and data chunks. When it finds FMT, it reads the audio format parameters like sample rate and channels, and when it finds data, it records where the audio starts. Unknown chunks like metadata are skipped, so this handles the audio files from different audio editors that might have varying chunk orders. Audio is read in fixed-size frames of 358 bytes, and in our case, this represents about 40 milliseconds of sound. Reading frames like this instead of the whole file allows streaming, so we can send and play audio progressively rather than wait for the complete download. And for the mechanism of the sender of the audio, the sender reads each frame, encodes it in base 64 for safe transmission, and sends it. After each frame, it waits for an acknowledgement, then sleeps for 40 milliseconds. This delay simulates real-time streaming, so we're not flooding the receiver with data faster than they can play it. For real-time playback, here we can see that the receiver opens a pipe to a Play Linux audio player, and as each frame is arrived, it's written to both disk and written to the pipe. And then the F-flush ensures that immediate playback is played without buffering. The audio is saved to the disk regardless, so user can play it later. Okay, so here I already have Alice, Bob, and Claire logged in, and for Bob, he created a group called Team, and then Alice is in that group, and she has sent some message, so Bob and Alice has actually messaged in the group. So here you can see Bob gets Alice message, "Hi guys, it's Alice," and then he sent back, "Hi Alice," which Alice got. And since Claire is not in the team, she didn't get any of the message. And let's see what happens if she tries to send a message to the group she's not in. So she gets an error, but let's join the group. So because Claire joined the group, the key is updated, and Bob and Alice is also notified of this. And also when Claire leave group team, Bob and Alice would know that the group key was updated. But even though Claire is not in the group, Alice can still send a file to Claire. So I have a readme.pdf here, and Alice is sending it to Claire, and as you can see, Claire successfully received readme, and then she got the received readme, and yeah, so log out. Okay, so what happens if Alice tries to do it again, but Claire is logged out? Send. Let's just chat Claire, hello, but the user is offline, so that's why she got the error. Okay, so there is actually a difference between the logging for group messages and individual message. So for example, if Alice now gives a message to Bob, chat Bob, hello, privately. This would be different from the notification that Bob got when Alice messaged him through the group chat. And here we have an audio file, so let's try to do the streaming of the audio file. Stream audio stream audio bob dot. So it's still a bit patchy because we do it so that Alice don't send too fast. But after Bob received the audio, he can play it again. Received audio, Alice. So that way, the audio is smoother. And because we already established the login register and stuff in the phase 1, so I don't want to spend more time explaining it. But in phase 1, we did get a deduction because one terminal can only be logged in by one person, so we fixed that. So let's try if Claire has 789. We get the error that we've already logged in as Alice, so we fixed that bug in phase 1. Thank you.